Welcome! In this session, we will dive into LeetCode problem number 589, N-ary tree preorder traversal. Together, we'll explore an efficient approach to solve this problem while understanding the concepts of tree traversal. Let's get started. In this problem, we need to perform a preorder traversal on an N-ary tree. An N-ary tree is a tree structure where each node can have up to n children, and n can vary for each node. In a preorder traversal, we visit the root node first, and then recursively visit each of its children in a left-to-right order. Our task is to implement a function that takes the root of such a tree as input and returns the traversal result as a list of integers. To help you understand the input structure, each node in the tree is represented by a node class. This class has two attributes, val, which stores the value of the node, and children, which is a list containing the node's children. If a node has no children, the children list will be empty. With this, you can visualize how the tree is structured and how the traversal should proceed. The output of this problem is a simple list of integers that represents the values of the nodes visited during the preorder traversal. To make this clearer, let's look at an example. Imagine we have a tree where the root node has a value of 1, and it has 3 children, 3, 2, and 4. The node with value 3 has 2 children, 5 and 6. The input can be represented using the node class, and the output for the preorder traversal of this tree would be 1, 3, 5, 6, 2, 4. This sequence reflects the order in which the nodes are visited during the traversal. We start at the root, visit it, and then move down to its children, visiting each one and their respective subtrees in a left-to-right order. To better understand how the traversal works, let's break down the example step by step. The tree structure can be visualized with 1 as the root, which has 3 children, 3, 2, and 4. Node 3, in turn, has 2 children, 5 and 6. The preorder traversal begins by visiting the root node, which is 1. Then, we move to its first child, 3, and visit it. From node 3, we proceed to its children, visiting 5 first, followed by 6. After finishing with node 3 and its children, we return to the root and traverse the next child, 2. Finally, we move to the last child, 4. This traversal gives us the result, 1, 3, 5, 6, 2, 4. By following the depth-first approach, we ensure that each subtree is fully explored before moving on to the next sibling. Now consider another example to further illustrate this process. Suppose the root node again has a value of 1, but this time it has 3 children, 2, 3, and 4. Node 4 has 1 child, 5. The output of the preorder traversal for this tree would be 1, 2, 3, 4, 5. Let's walk through this step by step. We start by visiting the root node, 1. Next, we traverse its first child, 2, and then move to the second child, 3. After visiting 3, we go to the third child, 4. Since node 4 has a child, 5, we visit it before completing the traversal. This example highlights how we always prioritize visiting a node and its descendants before moving to the next sibling. In this example, the final result of the traversal is 1, 2, 3, 4, 5. The process simply involves visiting the root, then each child from left to right, and recursively including their children when present. To further solidify this concept, let's consider a simpler case where the tree consists of just one node. If the root node has a value of 1 and no children, the output of the traversal would be 1. The process here is straightforward since there's only one node to visit. This is the simplest case of a preorder traversal. Finally, let's review some constraints and edge cases to keep in mind. The tree can have up to 10,000 nodes, and each node's value is unique and within the range of 1 to 10,000. If the tree is empty, meaning the root is none, the output should be an empty list. For a single node tree, the traversal will simply return the value of that node. Additionally, we must handle trees with significant depth, up to a maximum of 1,000 levels, as well as trees that are very wide, where many nodes have a large number of children. Efficient handling of these edge cases is crucial to ensure that the algorithm performs well and does not exceed memory or stack limits. To solve the N-ary tree preorder traversal problem, we first consider the recursive approach. This method directly mirrors the definition of preorder traversal, where you visit the root first, followed by its children in order. The process is straightforward: start at the root, add its value to the result list, and then recursively process each child node from left to right. This approach leverages the call stack to manage traversal depth, which eliminates the need for explicit data structures. In terms of complexity, we visit each node exactly once, so the time complexity is O(n), where n is the total number of nodes. However, the space complexity depends on the height of the tree, O(h), as the recursion stack grows with the depth. While this method is elegant and simple to implement, it has its limitations, especially with very deep trees where stack overflow can occur. This trade-off makes it less robust for handling edge cases involving extremely large or unbalanced trees. An alternative to recursion is the iterative approach using an explicit stack. This method avoids the limitations of recursion by manually simulating the function call stack. We start by initializing a stack and pushing the root node onto it. Then, as long as the stack isn't empty, we pop the top node, add its value to the result list, and push its children onto the stack in reverse order. This ensures that the leftmost child is processed first, preserving the preorder traversal order. The time complexity remains O(n), as each node is pushed and popped exactly once. Similarly, the space complexity is O(h) in the worst case, where h is the tree's height, due to the stack storing nodes at the maximum depth. The iterative method is slightly more complex to implement than recursion, but it's safer for deep trees as it avoids the risk of stack overflow. This makes it a more robust solution for handling large or unbalanced inputs. Given the trade-offs of both approaches, the iterative method emerges as the preferred strategy for this problem. Its primary advantage is that it avoids the risk of stack overflow, making it more reliable for deeply nested or very large trees. While the recursive method is simpler and more intuitive, it's less suitable for edge cases where the tree depth exceeds the recursion limit. The iterative approach, on the other hand, offers the same O(n) time complexity and comparable O(h) space complexity, but with greater control over the traversal process. A key insight that makes this approach effective is recognizing that preorder traversal is inherently depth-first, which aligns naturally with both recursion and stack-based iteration. By pushing children onto the stack in reverse order, we ensure the correct left-to-right traversal order. This systematic replacement of recursion with an explicit stack provides a robust and scalable solution. Ultimately, we choose the iterative approach for its robustness and ability to handle all edge cases. Its reliability in managing very deep or unbalanced trees without the risk of stack overflow makes it the ideal solution for this problem. While recursion offers simplicity, the iterative method provides better scalability and control, which are critical for ensuring the solution works across all possible inputs. To begin, let's break down the steps for performing a preorder traversal in an N-ary tree. Preorder traversal means we visit nodes in the order, root first, then the left subtree, and then the right subtree. This definition forms the foundation of our approach. To implement this recursively, we'll define a helper function, preorder root, where the root represents the current node. Now, the function needs to handle two cases. First, the base case: if the current node is null, we simply return. This ensures that we handle empty trees or nodes without children gracefully. Second, the recursive case: we process the root node by adding its value to our result list, and then we recursively call the preorder function for the left subtree followed by the right subtree. These steps ensure that each node is visited in the correct order as defined by the traversal logic. Once the recursive function is defined, the next step is to initialize and execute it. First, we create an empty list, result, which will store the values of nodes as we traverse the tree in preorder. Then, we call the preorder function, passing in the root of the tree to start the traversal. After the function completes, we return the result list, which now holds all node values in the correct order. It's also important to handle edge cases effectively. For example, if the tree is empty, meaning the root is null, the result should simply be an empty list. For a tree with only a single node, the result will contain just the value of that node. Unbalanced trees are naturally handled by the recursive logic, as the function will process all existing children while skipping over null nodes. Understanding why this approach works well requires looking at the recursive structure of trees. Trees are inherently recursive, meaning each subtree is itself a smaller tree. This makes recursion a natural way to traverse them. The recursive implementation aligns perfectly with the definition of preorder traversal since we process the root first, followed by recursive calls for the left and right subtrees. In terms of space complexity, recursion uses the call stack to keep track of the nodes being processed. The maximum space used by the call stack corresponds to the height of the tree, so the space complexity is O(h), where h is the tree's height. Finally, the base case in the recursive function ensures that null nodes, such as those in empty trees or leaf nodes without children, are handled seamlessly without requiring extra checks in the main traversal logic. Now, let's discuss the key data structures and operations involved in this algorithm. First, we have the result list, which stores the traversal output in preorder sequence. Appending values to this list is efficient, taking constant time, or O(1), for each operation. The second critical data structure is the call stack, which is used implicitly during recursion. The call stack keeps track of the current node being processed and its state. The maximum depth of the call stack equals the height of the tree, which gives us our space complexity of O(h). As for the main operations, they include visiting the root, where we add the root's value to the result list. Then, recursive calls are made for the left and right subtrees, maintaining the correct preorder sequence. Finally, the base case check ensures that no unnecessary operations are performed on null nodes, making the algorithm both robust and efficient. While recursion is elegant, it has its limitations, especially for very deep trees where it can lead to stack overflow. To handle such cases, an iterative approach can be used as an optimization. Instead of relying on the call stack, you can use an explicit stack data structure to simulate the traversal. This approach is more robust for larger input sizes. Another optimization is utilizing tail recursion, if the programming language supports it. Tail recursion can reduce stack usage by reusing the same stack frame for recursive calls, making the algorithm more memory efficient. These optimizations ensure that the algorithm remains scalable and performant, even for extreme cases. This implementation solves the problem of performing a preorder traversal of an N-ary tree. Let's break it down step by step. 1. Node class definition. The node class is defined to represent each tree node. It includes a val attribute for the node's value and a children attribute, which is a list of child nodes. If no children are provided, it defaults to an empty list. 2. Solution class and preorder method. Inside the solution class, the preorder method is defined. This method takes the root of the tree as input and returns a list of node values in preorder traversal order. 3. Base case. The first check in the preorder method handles the base case. If the root is none, i.e., the tree is empty, the function immediately returns an empty list. 4. Recursive preorder traversal. A helper function, DFS, is defined to perform a depth-first search, DFS, traversal recursively. The DFS function first checks if the current node is none. If so, it returns. Otherwise, it appends the current node's value to the result list, marking the node as visited in preorder. Then, it iterates over the children of the current node. For each child, the DFS function is called recursively. 5. DFS invocation. The DFS function is initially called with the root node. This starts the recursive traversal from the root of the N-ary tree. 6. Return the result. Finally, after the DFS traversal is completed, the result list, which contains the preorder traversal of the tree, is returned. This solution ensures that all nodes are visited in preorder, root-children, efficiently. The recursive structure of the DFS function mirrors the tree traversal process, making the code both simple and intuitive. The time complexity is O(n), where n is the total number of nodes in the tree, as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Here, we start by defining the node class to represent the structure of an N-ary tree. Each node has a value, represented by the val field, and a list of children, represented by the children field. We provide multiple constructors for flexibility, allowing us to initialize a node with just a value or with both a value and its children. Next, we define the solution class, where the preorder method will implement the N-ary tree preorder traversal. The method begins by creating an empty list result to store the traversal output. Then, we handle the base case. If the root of the tree is null, we simply return the empty list, as there are no nodes to traverse. To perform the preorder traversal, we call a helper method named DFS and pass in the root node along with the result list. The DFS method is defined to handle the traversal recursively. It begins by checking if the current node is null, and if so, it returns immediately, ensuring we don't attempt to process a non-existent node. Next, the current node's value is added to the result list, as preorder traversal visits the node itself before its children. Then, for each child in the current node's children list, the DFS method is called recursively. This ensures that we visit all children in the correct order, maintaining the properties of preorder traversal. Finally, the result list is returned, containing the values of the N-ary tree nodes in preorder sequence. In this example, we have a very simple tree with just a single root node having the value 1. The preorder function is called, and the first step is to initialize an empty list called result. This list will store the traversal order. Then, we call the helper function DFS with the root node as the input. Inside the DFS function, the value of the current node, which is 1, is added to the result list. Since this root node does not have any children, the DFS function returns, and the preorder function concludes by returning the result list. The output in this case is simply 1, as the tree contains only the root node. Now, let's look at a more complex tree structure that has multiple levels. Here, the root node has the value 1, and it has 3 children, nodes 2, 3, and 6. Node 3 further has 2 children, nodes 4 and 5. The preorder function starts the same way, initializing an empty result list and calling the DFS function with the root node. The value of the root, 1, is added to the result list. We then iterate over the children of the root node. The first child is node 2. The DFS function is called with node 2, and its value is added to the result list. Since node 2 has no children, the DFS function returns. Next, we process the second child of the root node, which is node 3. The DFS function is called with node 3, and its value is added to the result list. Node 3 has 2 children, nodes 4 and 5. We start with node 4. The DFS function is called with node 4, and its value is added to the result list. Node 4 has no children, so the DFS function returns. Then, we proceed to node 5. The DFS function is called with node 5, and its value is added to the result list. Node 5 also has no children, so the DFS function returns. With both children of node 3 processed, the DFS function for node 3 also returns. Finally, we move to the third child of the root node, which is node 6. The DFS function is called with node 6, and its value is added to the result list. Node 6 has no children, so the DFS function returns. At the end of this traversal, the preorder function returns the result list, which is 1, 2, 3, 4, 5, 6. The final output for this example is 1, 2, 3, 4, 5, 6. This sequence reflects the preorder traversal order, where we visit the root node first, then recursively visit each child from left to right. Now, let's consider an edge case where the tree is empty. If the root is none, the preorder function immediately detects this and returns an empty list. No recursive calls are needed in this scenario, and the output is simply. From these examples, there are several key takeaways. First, the algorithm follows the preorder traversal pattern by visiting the root node first and then recursively visiting each child in order. Second, the result list is used to maintain the traversal order, with each node's value appended during the DFS calls. Finally, the algorithm handles edge cases effectively, such as when the tree is empty or when nodes do not have children. These base cases ensure that the function is robust and can handle various tree structures gracefully. The time complexity of an N-ary tree preorder traversal is O(n), where n represents the total number of nodes in the tree. This is because during the traversal, each node is visited exactly once. For every node, the algorithm performs a constant amount of work to append its value to the result list, which is O(1). Additionally, the algorithm recursively processes all the children of the node, ensuring that each node is handled exactly once across the entire recursion. As a result, the total work done is proportional to the number of nodes, giving us a time complexity of O(n). This remains consistent across all cases best, average, and worst, because no matter how the tree is structured, every node must be visited to complete the traversal. Now, let's discuss the space complexity, which is O(h), where h is the height of the tree. The primary space usage comes from the recursion stack. In the worst-case scenario, where the tree is highly unbalanced, the recursion stack might grow to a depth equal to the total number of nodes, n. In this case, the space complexity becomes O(n). On the other hand, in the best-case scenario, such as with a perfectly balanced N-ary tree, the recursion stack's depth corresponds to the height of the tree, which can be as small as O log_n. However, perfectly balanced trees are rare in practice. It's important to note that while the result list also requires memory to store the output, it does not contribute to the asymptotic space complexity since it is necessary for the final result. Thus, the overall space complexity is determined by the recursion stack, making it O(h), and in the worst case, this expands to O(n). Let's compare this optimized approach to a naive implementation. A less efficient method might require multiple passes through the tree or additional data structures for intermediate storage, which could significantly increase time or space complexity depending on the design. In contrast, the current implementation is optimal. The time complexity is O(n), because each node is processed exactly once, and the space complexity is O(h), due to the recursion stack depth. Importantly, no auxiliary data structures are used, apart from the result list, which directly stores the output. This makes the implementation efficient and ensures it adheres to the optimal big O bounds for solving the N-ary tree traversal problem. When tackling the N-ary tree preorder traversal, there are several common mistakes to watch out for. First, forgetting to handle the case where the root is null or the tree is empty can lead to runtime errors, such as a null pointer exception, especially in recursive implementations. Always ensure you check for this edge case upfront. Next, in recursive solutions, the lack of a proper base case can cause infinite recursion or stack overflow errors. It's critical to verify that your base case handles scenarios like encountering a null node. Another issue is processing nodes in the wrong order. Preorder traversal follows the strict sequence of root, followed by left children, and then right children. Deviating from this order can produce incorrect results. Additionally, in iterative solutions, memory inefficiencies can arise if unnecessary nodes are pushed onto the stack or if stack management is not handled correctly. Finally, overcomplicating the solution is another pitfall. For example, using a queue instead of a stack for preorder traversal can increase complexity unnecessarily, making your code harder to debug and less efficient. Now, let's focus on some useful insights for interviews. It's essential to account for edge cases, such as trees with only one node, completely unbalanced trees where all nodes are on one side, or large trees where recursion depth could cause stack overflow. In such cases, iterative solutions are often more practical. Common follow-up questions include how to modify the algorithm for postorder or inorder traversal, or how to approach the problem iteratively instead of recursively. You might also be asked how to optimize space usage for skewed trees. Remember that preorder traversal aligns with a depth-first approach, which is key to understanding its structure and behavior. While recursive solutions are typically cleaner and more intuitive, iterative methods are preferred for very deep trees to avoid stack-related issues. Being able to articulate these trade-offs will demonstrate your depth of understanding. To deepen your understanding, it helps to explore related problems. For example, binary tree inorder traversal on LeetCode number 94, postorder traversal on LeetCode number 145, and level order traversal on LeetCode number 102 all build on similar traversal concepts. Another interesting challenge is constructing a binary tree from preorder and inorder traversal, as seen in LeetCode number 105. Beyond that, there are alternative approaches to consider. The iterative preorder traversal method uses an explicit stack instead of recursion, giving you more control over memory usage. However, this approach requires careful management of the stack to ensure nodes are processed in the correct order. For instance, when pushing nodes onto the stack, the right child should be pushed first so that the left child is processed immediately after the current node. This implementation is particularly useful for avoiding recursion-related stack overflow in large or deep trees. Another advanced approach is Morris traversal, which eliminates the need for extra space, such as a stack or recursion, by temporarily modifying the tree structure. This method uses the concept of threading to traverse the tree. While it's space efficient, it is more complex to implement and less intuitive to understand. The idea is to establish temporary links between nodes to facilitate traversal without additional memory. For instance, when a node has a left child, you identify its rightmost descendant in the left subtree, known as the predecessor, and create a temporary link back to the current node. This allows you to visit the node later without needing a stack. However, it's essential to restore the tree's structure after traversal to maintain its integrity. While Morris traversal is not commonly required in interviews, knowing this technique can help you stand out by demonstrating your ability to think beyond conventional solutions. Great job! To recap, we solved N-ary tree preorder traversal using a recursive approach. Remember the importance of understanding traversal orders and their trade-offs. Thank you for joining, and make sure to subscribe for more problem-solving walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!